When we talk about loop tuning, the first thing that comes in our mind is PID tuning. But PID tuning is just the tip of the iceberg. So if the loop tuning is an iceberg, right? So PID tuning is just the tip of the iceberg. Below that, there are so many things. You need to know your process. You need to know the condition of the instrumentation system. You need to know what kind of instrumentation, whether it is pneumatic or whether it is electronic, whether the process is self-regulating type or process is integrating type. All these things you need to know to do a proper loop tuning. In this particular lecture, we will be giving you the step-by-step guide so that you can independently tune a loop, a process loop, without the issue of the stability, without the issue of oscillations and other problems. So let's begin. So if you see all the process, there will be a controller, and loop tuning begins with the controller. This is our primary focus because we want to tune the controller. So in a closed loop, the controller sends output to the final control element, right? So this is known as final control element. Now the final control element can be a valve, it can be a dampener, it can be any other thing. Now even the control valve, it can be globe type, it can be rotary, it can be single acting, it can be double acting. So there are so many different things that may happen within this final element. And depending on the type of the final control element, your tuning may get affected sometimes, right? And when you change the output to the valve, the change in the process is measured by the transmitter, right? So change is measured by the transmitter and it feeds back to the controller. So controller sends the signal to the final element and gets the feedback through the transmitter. Now the controller, if the controller wants to move from one condition, one stable situation to another stable situation, it need to change the set point, and set point, this is given by human, right? Or you can say the operator. Now there's techniques where if it is in adverse process control, then set point may come from some other systems like adverse process control system. So what are the steps that we need to follow, right? First is know your process, understand your process. So whether it is self-regulating type process or it is a integrating type process. So if it is temperature, pressure or flow, it is self-regulating type, right? So self-regulating type is your flow, your temperature and your pressure, right? And integrating type is your level. So you have to understand the process, you need to understand your instrumentation system. Now you need to do a bump test, then model the system. After modeling, tune it. Then whatever you have tuned, validate it whether it has been tuned properly or not. In this particular lecture, we will be going through all these 5 steps and try to understand how this really happens. So first thing is know your process. How you will know your process? It can be through PNID, it can be through PFD. You may look into the data sheet of the valve, right, to understand what kind of positioner it is, whether it has a positioner or not, whether it is a globe kind of a valve or it is a rotary valve, or is there a control valve or there is a diverter or dampener in place, and what kind of process it is, whether it is a flow, level, pressure, temperature, what it is. So you need to understand your process. And in some cases, it makes sense if you visit the site also. So sometimes what happens that these control valves are there for years after years and they are in the degraded condition, right? So even if you tune the loop, I mean you will not be able to tune the loop with that with some degraded or control valve. Yeah. So you may go on days after days trying to tune your loop, finding that it is never happening. But a visit to the site confirms you the condition of the valve. So if you are tuning remotely, you can take help of the site person and ask them to go and visit the particular loop, whether the condition of the control valves and everything is fine or needs some maintenance. So this is the first step. When you know the process, you know the instrumentation, then so in this step, we'll be doing the bomb test. In the bomb test, what happens is first the controller is put in the manual state and the final element is moved by a step, right? And when you do a step change in the output or the valve, what will happen? There will be a change in the process, right? And the change is measured by the transmitter, which is in the process line, and we can have a plot time versus the measured variable, right? And from this plot, we will know two things. One is process gain and another is time constant. So, so if you see that this is a settling stage and this is again a settling stage, so time between these two is basically 4 times your process time constant. And the slope of this curve, right, this will give you this is delta mb by delta t, so how it is moved, and this delta mb divided by, if we call it delta u, this will give you the process gain. So these two parameters basically signifies this process. So process gain is how much did it move, and process time constant is how much time did it take to move, right? So the time you can see from settling time to again settling time, this time difference is basically 4 times the time constant of the process, and the change in the measured variable divided by change in the output, that gives you process gain. Now after bump test, the next steps is comes as tuning, right? So in the tuning, obviously the things that comes to your mind is PID, and there are different types of PID: standard, parallel, classical. And again, the PID equation or the nomenclature is varies from vendor to vendor. So if you use one vendor against the, here I am not mentioning any vendor's name, but if you are using one vendor against another vendor, you will see they will call the same thing in a different way. Some will call proportional gain, some will call proportional band, and the proportional band and proportional gain can be totally two different things. So just be careful, read to the manual of the DCS vendors to know what they actually mean. But uh, textbook wise, there are 3 different types of equation, and the same equation you will find in most of the DCS vendor. The equations are standard, parallel, and classical, and you can see how they are different, right? So in one case it is Kc into 1 plus Ti into S into TdS. Another case it is Kp Ks. So look for the parenthesis, like look for the parenthesis to know the difference, right? So so when you check the equation in your DCS vendor's manual, you also check for this. So now the tuning, how we will do the tuning. There are basically two methods of tuning. One is Jiglan-Nichols and another is uh, direct synthesis. Jiglan-Nichols method was uh, was there for a very long time. It was developed in 1940. But this particular method, this Jiglan-Nichols method, is more useful when you have a pneumatic controller and pneumatic instruments, because the pneumatic instruments are not so precise and there is a lag in the transmission line, right? So, so that's why I would say for modern day electronics transmitter and digital controller, it is better to use direct synthesis technique, right? So in the direct synthesis technique, what is done is basically, so before even going into the direct synthesis technique, what you need to do is when your controller is in auto. So earlier you remember when it was the bump test was done, your controller was in manual, right? And you have basically in the valve you have done the output change, right? Now what you are doing, your controller is in auto and you are changing the set point. When you are changing the set point, notice how much your MB has moved, right? So this MB, this delta MB by delta SP, this will give you uh, the closed loop gain. This will give you the closed loop gain. So this has to be done even into going this direct synthesis and the Jiglan-Nichols technique. And this will also give you the closed loop time constant. So these two are really important. So for example, for in this case, uh, our delta MB by delta SP is equal to 1. Next is, okay, so when you get the closed loop gain and the closed loop time constant, now it is time to use the direct synthesis and the Jignan-Nichols technique to identify the tuning parameters of the PID controller, right? So, so what happens in the direct synthesis technique? There are these mathematical equations. So there are many calculation behind it, but we'll be just using the set of equation to for our purpose. So for example, in this case, the controller gain will be 1 upon Kp into R, where Kp is your process gain and R is your speed of response. And speed of response can be chosen 1, 2, or 3, right? Where 1 is, I would say, fast and this is slow. Again, this fast and slow is with respect to your current process, right? And the integral time is the open loop constant which we got from the bump test, right? And with this, when these parameters are known and you have pi and pid, right? So you know what is your values, right? You know what is your controller gain, this is your ti, and this is your td, right? So you need to, from this you will get all these values, right? And then you need to put it into the controller and then see what is the performance of the controller. So for this particular lecture, we are not going into details of the direct synthesis technique and Jiglan-Nichols technique. There are other videos that are mentioned in the description box. If you want to know in details how this direct synthesis technique works, how the Jiglan-Nichols technique works, you can go and check in that videos. Now, when so after you set your controller with this parameter, then you need to validate it, whether your system is really behaving like that or not. So again, what you can do a step change. and uh, you can measure how much time really is it taking. So if you see in this example, so this is like Kc is 1 by Kp into R, and if we choose Kp is 6, and we take a first response, so R is equal to 1, so Kc will be 1 by 6, right? So this is the gain, the closed loop gain will be 1 by 6, and your Ti will be T open is equal to 12, right? So in that case, you should, when you do a step change, you should take at least like, it will take uh, 48 seconds to reach to uh, the set point level, and this is known as a validation. So hope you have understood the process. So first know your process, right? First step, then do the bump test. This is basically the open loop bump test. Then do the modeling, then do the tuning, and at the last do the validation. If you do loop tuning in this way, then obviously your loop tuning will be very stable and you will not come across much of the issues in the future. Thank you.